and most of the new things I'll mention are joint work with Robert Bredereck, Jehua Chen, Stephen Kratsch, and Rolf Niedermeier from Berlin, and Gerhard Woeginger from Eindhoven. And this will be a problem, an extremal problem in combinatorial geometry. And its analysis combines some combinatorial arguments with geometric ones and tools from discrepancy theory and linear algebra. But actually just a little bit of anything. So I think I'll be able to more or less explain everything, but we'll see. Now I want, before stating the problem, I want to give you some motivation, because otherwise the problem may look a little bit artificial. So the motivation comes from the theory of social choice when we deal with elections. And here is how it goes. So imagine that you have some elections. So you can think about your favorite elections. I'm thinking about, say, the elections for parliament we had in Israel in last January, right? So at least in Israel, the rules are like this. The parliament members are elected, and then the president consults with representatives of the parties. And then he chooses the person that has the maximum chances in his view to be able to form a coalition, to have the support of a majority. And then this person gets 28 days to try to form a government, to get the support of majority. And if 28 days are not enough, so if he doesn't succeed in 28 days, he may get 14 more days. And so the total is 42. And that's it. So if he doesn't succeed in 42 days, then either the president chooses someone else and asks him to try to form a government, or there are new elections. So there are and the results in Israel of the last elections were pretty decisive. So it seemed more or less clear already from the beginning who will be in the government. And still, it took 41 days. So there was only 1 day left. And then you may wonder why is it so difficult? So I'll try to give some mathematical simplified model, and we'll try to understand why is it difficult. Okay, so how is it usually done? We have this. So we have a parliament. So I want to describe some model. We will have n parliament members. And then we have all kinds of issues which they can either support or object, right? So let M be the number of issues. So you can think about, I don't know, cancel the Second Amendment, increase taxes, decrease or erase the value-added tax, limits the size of the government to 18 members, whatever. Right. So these are issues. Yeah. Question. So M and N could be arbitrary. Usually we will have M eventually bigger than N, but it's not necessarily. It can be much smaller also. So yeah, the trouble is that if people keep coming, they will miss the motivation. But okay, so let's say, yeah. Anyway, it will. All right. So we have these M issues, and we can form a matrix. So we will have A will be some matrix Aij. It will be n by M, and each Aij will be either -1 or 1. And of course, this tells us if member I supports or objects issue j, right? So a I j equals 1 if and only if a member I supports issue j. Okay. Now, what this prospective prime minister should do, he should choose an agenda. An agenda consists of a subset of the issues. So what he wants to suggest, so this will be an agenda. It will just be some set Q, which is a subset of M. M in brackets denotes always a set of all indices of the columns, the integers from 1 up to M. So this is the agenda, and the prospective prime minister tries to choose an agenda that will have the support of the majority. Now, I'm going to assume two simplifying assumptions. I think in some countries they are true, maybe in some countries they are not, but so you can decide if you believe them or not. So one of them is that the parliament members are very simple-minded. They support, they like an agenda, if and only if they like more than half of the issues in it. So they go by majority. Afterwards, we'll consider maybe weighted case, but let's think about this. And the second one is that this prospective prime minister, he doesn't care at all about the issues. The only thing he cares about is to have the support of the majority, right? So he wants to choose an agenda that will be winning, will have the support of more than half of the parliament members. So let's say that Q is a winning agenda. If and only if the number of parliament members I, so that the sum of Aij, j in Q is positive, right? This is positive. This exactly means that member I supports the agenda, Q. He likes more than half of the issues in it, if this is bigger than n over 2. Okay. So these are the definitions, and indeed they, according to this model at least, so now there are no parties, but afterwards it doesn't really matter much if you think about the parliament members as parties and not as members. So, but let's now leave it like this. So the computational problem that this prospective prime minister has to address is, given this matrix A, is there a winning agenda? Okay, so this is so here are some results. First, something that I'll not talk about, but let me just mention it. So this will be the first proposition, and this says that deciding if there is a winning agenda is computationally a hard problem. Maybe it's not so surprising. So given A, again it will be n by m, and it will be a matrix of plus minus ones. Maybe I'll not write it all the time. All my matrices always will be plus minus 1 matrices. So deciding if there is a winning Q, a winning agenda, is NP hard or NP complete. Of course, it's in NP.
There's no requirement on the size of the agenda, yes?
No, yeah. So it can be any subset, right? So that's what we said, that the prime minister does not care about the issues. He just wants the support of the majority. Right. So it can be any subset. It can be one issue. It cannot be 0, right? Because we want really to be positive. So it can, right? Okay. So this is NP-hard. On the other hand, it's but is what is called a fixed parameter tractable. As I said, I'll not talk much about this, but let me mention it anyway. So fixed parameter tractable with respect to the two natural parameters. With respect to either, well, one of them is trivial, I'll say what this means. So either m, this is trivial, or n, this will follow from what I say. So fixed parameter tractable means that if the parameter is small, then there is an efficient algorithm, or more precisely that the problem can be solved in time, which is some function, any function depending on m, let's say, times a fixed polynomial in the size of the input, or any function depending on n times a fixed polynomial in the size of the input. So for example, this is trivial. There is a trivial algorithm in time, running in time, 2 to the m times, say, n times m, right? Because we just try all the possible agendas, that are all subsets, and for each of them we check. So this is the other one is not obvious, but it will follow from what I say. So there is we can solve it also in time, which is some function of n times m, maybe. Also, it's linear, the other. So if the number of parties or the number of parliament members is small, then also the problem is simple. And there is, even for those that are interested in fixed parameter tractability, there is even, it will follow from the proof, there is what's called the kernel for the problem that is small. Namely, we can always, given an instance, we can, in polynomial time, convert it to an instance whose size will be bounded by some function of n. And the new instance will have a winning agenda, if and only if the old instance had one. So really, we don't care if n is big. Okay, but it's not. But what I'll be more interested in, maybe somewhat related to what Yael asked, I want to know how large or how complicated can the winning agenda be, if there is one. Can it be very large? Can it? Okay, and so let's denote by G n m. So this will be the minimum number G, so that for every n by m, so for every a as before, with a winning agenda, a winning Q, there exists a Q which is not so big. Okay, so there exists such Q, maybe call it Q prime. So again, a winning agenda which is of size at most G. Okay, so if there is a winning agenda, there is one that is small. And then I want to wonder how big can it be if the number of parliament members or parties is n. Now we don't specify the number of issues. It can be arbitrary. So I write here the supremum over m of G and m. And note that it's not obvious that it's finite at all. So it could, and you need, in fact, some, it will be finite, but you need some argument even to show that this is finite at all. All right, so in words, I'll not write it, but just say it. This G of n tells us how complicated or how big can the minimum winning agenda be when we have n parliament members, if there is a winning agenda. Right? So if this is very big, it also assigns that this is kind of complicated. So you can check for small values of n. It's not too difficult to compute G. Just and although, despite the fact that I said that to show that G of 20 is finite, you need to think. So, but just to compute the small ones is not difficult. And let me give you some of them. So I'll not. I just so can show, and not difficult to show, that G of 1 is G of 2 is G of 3 is 1. G of 4 is equal to G of 5 is 3. G of 6 is equal to G of 7 is 5. And I think you can more or less guess the pattern here. And this is one theorem that I want to show you in the paper with these co-authors, that the asymptotic behavior of G of n as you can guess from these few cases that you see here, is n raised to the power n over 4 plus little of n. Okay, so it's finite, it's pretty big, right? And we kind of understand it up to the low order term in the exponent. So n is the number of parties. Say that again.
If n is the number of parties in Israel, it's 41.
It's 41. What's the 4?
The number of days, not the number of issues.
No. Okay. Yeah, that's a number of issues. Okay. So the number of parties in Israel now is 12 in the existing parliament, and that's more or less normal for the last few elections in Israel. And for 12, so I didn't, because of asymptotics here, I didn't check, but it will be a big number, so significantly more than 41, definitely. But so it is on the other, okay, but for parties it's a weighted case, so in a way, but never mind. Yeah, it's all right. Okay, so I want to say something about the proof of that, and actually it's related to several things that I'll mention during the course of the proof. So let me just now give the related things. So proof related to proof and also result related to problems and results in the following things. So the first one is there are some results by Huckeman, Jurkat, and Shapley. They also had some motivation from game theory, and this is about something that they call indecomposable hypergraphs. So right now I'm only saying the buzzwords. Hypergraphs. And these are old papers, basically from the 70s. Then there is a paper by some work by Graham and Sloane, and this is about something that they call anti-Hadamard matrices. Right, so this is sometimes in the 80s. I should say that all these papers, they raise some problems and they give some results. They don't really get kind of precise asymptotic solutions to them. This came later, but I'll mention it. So anti-Hadamard matrices, a Hadamard matrix is a plus minus 1 matrix, which is essentially the inverse of itself. Every two rows are orthogonal. And this means that if you look at the inverse of the matrix, then every entry will be in absolute value 1 over n. And that's the smallest it can be for a plus minus 1 matrix. You can, non-singular, you can easily convince yourself. So anti-Hadamard matrices will be, this is how they call them, will be plus minus 1 matrices in which the entries of the inverse, or some entries of the inverse, are as large as we can, or as a condition, equivalently, it says that the condition number of the matrix is as bad as can be. So it's very non-stable, and we want to understand how large these entries can be. So these are, and then there is a construction by Hastad, and this is about threshold gates. Requiring large weights. So these are basically hyperplanes that separate in some way the vertices of the n-dimensional cube, the plus minus 1 to the n-dimensional cube. And we want such hyperplanes so that whenever we write them with integer coefficients, some integers will be very large. Okay? We want to understand how, so this is what Hastad was doing. This was 93 or something. And it's also related to some paper of Van Wu and myself, and which basically is motivated by a certain coin weighing problem. But also studies these earlier problems and give some new results about them. Okay, but I'll try to show you the proof more or less from scratch. Yeah.
The question about your model seems like, so your notion of a winning agenda is such that adding some element to the agenda, adding some item to the agenda can win more support or more anger from representatives, but leaving something out of the agenda doesn't generate anger or goodwill. And I just wondered if that choice.
Why? So you're saying that leaving something.
Sum over J in Q times Aij, but it's you could also consider, your agenda to be, I'm supporting these things and I'm not supporting the others. So you might think of a scoring rule where you have where Q is represented by a plus or minus one vector, and then you
Okay.
dot product of that vector with each one of these.
Right, so I prefer to think about it that I'll have an issue which is a negation of the issue that, so objecting an issue, like giving it -1, is like supporting the negation of the issue, right? So let's add that also. So it means I'll always prefer to have an issue and to have the negation of it also, and then if you prefer to put that in the agenda, then you can do it. Right, so that will more or less correspond to the same.
It doesn't answer his question, because if you leave both the issue and its negation, some people may be mad at you just because of that. So that's not in the model.
Okay,
Yeah.
that could be. So that's not, all right, so maybe I didn't understand. Right.
It doesn't capture
So the model is somewhat
how important
simplified.
issues are,
Yeah, I'll
how
say,
people care
right,
about
very
some
good,
issues
yeah.
being in the agenda at all.
That's right, and I'll say at the end at least something about when the different issues have different weights. So that's maybe natural. And then things, so definitely one can deal with this also, but then things become difficult computationally very, very early. So somehow it is, but I'll mention it at the end. So somehow.
That's why it takes 41
Okay,
days.
but yeah, okay.
So
So
you
it
are
will.
going to offer a model of Bibi when you started talking, sorry.
A model of?
Bibi.
Of Bibi, right, yeah. It will, so I didn't decide yet how far I'm going to go with this, but I could. I mean, but we'll see. All right, so, okay. So I want to start by describing the upper bound. The upper bound will be geometric. It uses some basic facts about Hilbert bases of cones, but I'll do it essentially from scratch. So it's some linear algebra, and so proofs. All right. So first, I want to change the problem about G to a problem about F that will be somewhat simpler to analyze. And let's define. So f of t will be the maximum now, or yeah, I mean, I could write supremum. It's really a maximum because again it's finite, but again it's not obvious a priori that it's finite. So it's a supremum of the integers f, so that there exists in t by f a, which is aij. Aij again is plus minus 1, each of them. Maybe I'll write it in words. A sum of columns of this matrix is positive in each coordinate, but in fact we can assume that is exactly the vector j, which is the all one vector. Okay, so this is the sum of columns. Yeah, so the sum of columns is 1 in each coordinate, and it's minimal in the sense and no proper subset of columns columns has a positive sum in each coordinate. Positive sum in each coordinate. So it's pretty similar to what we had before. Kind of here, you want to say maybe you want unanimous, so you want everybody to support. The agenda consists of everything. You want everybody to support it, and you want it to be a minimal agenda that everybody supports. Right? So this is and it's easy, so I'll not let me just state it. It's easy to see that g of n for every n, so this is the thing we started with, is exactly equal to f of n plus 1 over 2 ceiling. Right, so really, you just kind of, so maybe I'll just, okay, e.g. F of 3, for example, one can show that it is 3, so believe me. So this is here is a matrix, something like the identity matrix. So these are the columns. The sum of the columns is a all plus vector, and you see that it's minimal. If you don't take all the columns, you are not positive in all coordinates. And of course, if you have that f of 3 is 3, then it's obvious that g, so it implies that g of 3 is at least the same that g of, sorry, that g of 5, say, g of 5 is at least f of 5 plus 1 over 2, that 3, which is 3. And this is just because I take the same, right? So plus plus, and I'll add maybe 2 rows of minuses. And if you want it to look more, I don't know if this will, if you want it to look more complicated, let's add this. So this is some matrix of issues and parliament members, and there is here a winning agenda, namely the agenda consisting of the first 3 columns. And this winning agenda is winning because it has support of majority in at least 3 places among the 5. So these are these 3 places. And because this is minimal, there is no, right, we cannot do better. And you can convince yourself that it goes the other way around also. So again, one needs to think 2 minutes, but it's not complicated, it's not too interesting. So I'm just saying this is the same problem, and it's easier to think about this problem. So now we have just vectors of plus minus 1s, t-dimensional vectors. Their sum is all one vector, and no subset sum, no proper subset of columns is positive in all coordinates. And we ask how large can the number of vectors be. And you see the vectors are not necessarily distinct, because we will see, as I mentioned before, g of n is more than 2 to the n. Right? So we have repetitions. We really have issues that have exactly the same support, and let's feel it. Okay, so this is easy, and therefore the theorem is really equivalent to theorem prime that f of t is equal to t raised to the power t over 2 plus little o of t. So this is what we want. Yeah.
On fixed intuition. So the problem is symmetric with respect to positive and negative. So if you took absolute values, then you
it's symmetric in the sense. So now you want like a losing agenda, or how shall I change?
You put absolute value about. You ask the same question about the weights of negative.
I mean, it will obviously be the same if I'll ask if a losing agenda, if you want to, will be something that that the sum is negative in more than half of the coordinates, and the same question will be. But
computing cut norms.
Okay.
Whether you're given a matrix, and so the issue is the cut norm of the matrix the issue?
So I don't think so. So I really care about like one-sided cut norm of some sort, right? So I want And also it's not cut norm in the sense that I insist that I'll have more than half of the rows and any subset of columns. In there I have to be positive. I mean, the only thing is that I really, that is similar to cut norm, is that I really sum a subset of a sub-matrix, but I think it's not, yeah, and we care about signs, right? Okay, another, yeah, I should say that one.
problem has two majorities in it, but there is really one majority. The other majority is really unanimity.
You mean that maybe there are many winning, many,
no, but,
or?
Yeah, I mean, what they want is that all issues.
Ah, okay, right, yeah. So the other question, if you want to think
all
about
members,
it and say,
all members.
yeah, all members,
All members,
so you want a unanimous, yeah, so maybe you are in the,
only
inside the
majority
party.
is how many of the issues in the agenda you are for and how many you are against. That
Right.
determines whether you are for an agenda. That's the
Right.
majority part.
Yeah.
And then you want unanimity.
Yeah.
So it looked initially like a two threshold circuit, but now it's end of threshold.
Okay, okay, I agree. So now we, yeah, so if we want indeed to keep this intuition, then we now want to be unanimous, or indeed if it's a depth 2 circuit, we want an AND gate of majorities, and before we wanted a majority of majorities. That's fine. Okay, but yeah, it's kind of, and yeah, and I wrote it here that this sum is exactly 1 and not positive in each coordinate, but this you can easily convince yourself that it's the same. So it really doesn't make, so I could have defined it anyway. So, right, so we want to prove this. This thing, and I want so I want to say some things about bases of cones in Hilbert space. So here will be the first lemma. So if U1, U2 up to US are vectors in Rn, let's say, and are non-zero vectors, it will be convenient, and let's say that they are distinct. Okay, so we want to define a cone, so the cone will be C. It will be the set of all x1 up to xs, reals in Rs, so that the sum of xi ui is a 0 vector, and all the xi's are non-negative. It's a cone, it is closed under addition and under multiplication by positive or non-negative numbers. And let me, I want to define, so I could have defined it outside the lemma, but let's do the definition inside. So x that lies in C is called basic if for the support of it, so let I be the support, namely all the indices I, so that xi is strictly positive. I want that the vectors ui, I in I, so one way to say it, are finely independent. There is only one dependence between them. You see, we have some dependence between them, right? The sum of xi ui is equal to 0, and I want that this will be the only dependence. One way to say it is that they are finely independent. So this is a basic thing, and in particular, for a basic thing, the number of non-zero xi's cannot be too big, right? So it cannot be bigger than n plus 1 because they are finally independent. Now the claim is that, so far this was a definition, so the claim is that any, for all z that belongs to C, so now it's a general thing, I want to express it as a linear combination with positive coefficients of basic points. Okay, so there are y j, belongs to C, J in J, some index set, such that Yj is basic, and Z is a sum of Bj Yj over J in J. Bj's are positive, so I take the ones, yes, I guess I should have written here for every Z which is not a zero vector. So it's sum with positive coefficients of basic solutions, and the number of these basic things is not too big. This is what I want. And not too big means that J is strictly less than the support of Z. So the number of indices I, so that Zi is positive. Okay, this is so this is the claim. And in particular, so that implies in particular that J will be less than S, right? So S was the length of Z. Maybe all of it is in the support, but we never need too many basic things to express Z. And why is this true? So, so some linear algebra. So we'll prove it by induction on the size of the support. Okay, so proof, induction on L, which will be the size of the support I, so that the I is positive. So the smallest the support can be is 2, right? Because the vectors are distinct. We want, so if L equals 2, Z itself is basic, right? Because any two vectors, they are distinct vectors, so they are affinely independent because they are distinct. So Z itself is basic, and therefore we are fine here. So and now induction step. So if Z basic can still be basic, then and of course it's okay. Now, so assume not. Really matter. Now look at this Z. The claim is it's 0. So let me put I don't know. I will be the support of Z. So it's always I is such that Zi is positive. Now 0 is in convex hull. Of those vectors of Ui, I in I, right? Because the Z exactly tells you it's a linear combination. The sum of Zi, sum of Zi Ui equals a 0 vector. I in I, and we can normalize it to see that it's a convex hull, right? So I have it. So 0 is in the convex hull, therefore it's also in the convex hull of some minimal face of this polytope, the convex hull of these UIs. And this minimal, the vertices of the minimal face will be affinely independent. So this will be a basic thing, a basic point. So okay, so there exists a minimal, I, maybe I prime, that contain in I, just minimal with respect to containment, say, if you want, so that 0 is in convex hull of those, of Ui, I in I prime. So we have some some sort of solution 0 is the sum of maybe, I don't know, W I U I in I prime. Okay, this is just to say that, and these are this W is basic, right? Because the UIs are affinely independent, otherwise it won't be minimal. So W1 up to WS, W is basic by minimality. And now we can subtract some, so can subtract a multiple. Yeah, I should have said here that all the WIs are positive. Right? And now we can subtract some multiple of this equation this from Z, from the sum of Zi Ui equals 0, I in I, and we just subtract it, we subtract the biggest that we can, keeping all the Zi's still non-negative, and at least one of them will vanish, right? So we just multiply by the biggest numbers that we can still, so it's like the minimum ratio between an index of Z and an index of W. So we can subtract a multiple of this to get a point with a support of size at most L minus 1. Maybe we lose more if there is equality. Okay, now we use induction. So this is true. Okay, so this is the first lemma, and then
there was some motion after previous Tuesday talks to have a break.
Sure.
More interested.
Yeah, yeah.
So
it's
up to you to take 5 or 10 minutes.
yeah, I will. I mean, of course, we are all aware of the dangers here, but it's true. We'll give people opportunity to leave also. So let me. I wanted to try to finish the upper bound. So so the break will be in about 15 minutes, something. But okay, don't be nervous. If you okay, so it is right. If t is less than t to the t over 2 plus some, it will be exactly, actually, the upper bound that we'll get will be t plus 1 raised to the power t plus 1 over 2.
To get an upper bound is a constant times t to the power t over 2, a loose upper bound.
Okay, so a loose upper bound, so I know, okay, you're asking if it's simpler or if it's...
Yeah, can you use your trick there to complete, put enough minus?
So the trick, you mean the lemma or not the lemma?
No, proof theorem prime, weaker version that f of t is less than
Anything.
4 times t
Okay.
to the power t over 2.
So I know a different proof. So as I said, anything will need some proof. So I know a relatively short proof based on some result of Sebastianov that maybe I'll say it's that if you, but will not write it, it's that, so this will give some bound of the form 2t raised to the power t. But that's also, it's a nice thing that one should prove that if you have vectors in RT with respect to any norm, so that their sum is 0, and each of them has norm at most 1, so here we'll take the L infinity norm, then you can rearrange them, you can rearrange the vectors, so that every initial sum will have norm at most t. That's not a trivial theorem, but it's a nice thing.
Oh, so you will complete your vectors, that's why it's 2 times t. You extend the vectors to satisfy those hypotheses.
Yeah, I'll add the minus. Yeah, I still have to say something. So I'll add one vector which will be minus j. Then the sum will be 0. Then I'll rearrange them. Then I'll use pigeonhole, and then I'll get something. Yeah, so that will give some loose bound. And that's, I think, the shortest way I know to prove that it's finite. But so I think that even to prove that it's finite, you need some, I don't know, a very simple argument. Well, I mean, this is not very difficult, but I don't know. I don't know one line argument. So let's have another. Another lemma. Okay, so it will be a lemma 2. So lemma 1 is the vectors were general, but our vectors are plus minus 1 vectors. So now I want to say something about plus minus 1 vectors. So if u1 up to us are in a, okay, are again in a, well, maybe we're right, in plus minus 1 to the t. Okay, so they are now vectors of plus minus 1s. A c is as before, c cone as before. So all the x1 up to xs, so the sum of xi, ui is 0, and the xi's are non-negative. And a y that belongs to C is basic. Then we can write y. So y is some, you remember that for a basic thing, there is only one linear dependence. So y up to scaling is determined, is one vector. So y is some constant times w with w in C integral, right? So the constant C is positive. Okay. With w in C integral having integer coefficients, and the L1 norm of w is not so big, so is at most, the proof will give t plus 1 raised to the power t plus 1 over 2, and I'll write here, it's a lower order term, but I want to write it because then the upper bound will look nicer, so it will not. Okay, so the L1 norm of this w is essentially t to the t over 2, right? So for any basic. And why is this the case? Okay, so the proof is that there exists in P. So we have these affinely independent vectors. So we have really some P by P plus 1. P is at most T. You can think about T if you want. So really we have T plus 1 vectors. But theoretically we can have less vectors. So yeah, it will be some Hadamard inequality basically, and Kramer, but yeah, so I'll do it. So there exists some P by P plus 1, which P is at most T, matrix B with plus minus 1 entries. Bij is plus minus 1, so that B times y is 0. Right, this is the only linear dependence between those affinely independent, right, in the rank of B is P. So it's a full rank. And therefore, we can see either by Kramer or by the definition of determinant that what is a solution here. So we'll claim that a solution here, so up to scaling there is only one solution. A solution here, and you is the following. So it's really a minus 1 to the I plus 1 the determinant of bi, I'll define what that is, as I goes from 1 to p plus 1, where the determinant of I is, where bi is b mine without column number I. All right, so this follows from Kramer, but actually it's simpler to see it just from the definition of determinant, namely if you write the matrix B here, so this is a matrix, a P by P plus 1 matrix, maybe P plus 1 columns and P rows, this is B, and now you put here any row of B, so put row number J of B. I don't know if that's a good notation, so this is just this row. Then this determinant, this is a P plus 1 by P plus 1 matrix, and its determinant is 0 because it has 2 repeated rows. And if you expand it by the first row, then you see that you get the coefficients of the entries of this row times the minors, right? So the minors are exactly what you see here. So this vector here is orthogonal to row number J, and this holds for any row, so this is really the solution. Okay, but you can get it also for Kramer's rule. And so these are integers, right? But actually, if I want the smallest integral solution, I can divide also by the GCD of all of them, the greatest common divisor of the determinant of all the B sub I. Right, so this is kind of the minimal integral solution. If we divide by the GCD, any other solution is a scalar multiple of it. Right, so this is and now we want to know. So we have to estimate the L1 norm of this, right? So by adding to B another row with correct signs. So let's see what this means. So if I add, then we get that it will imply that the sum of the absolute values of the determinant of Bi is at most P plus 1 to the P plus 1 over 2. This will be Hadamard inequality. Right, because I add a row of plus minus 1s depending on the signs of the determinant. So this will make, if I expand by the first row, then each minor will become the absolute value of the minor. And the Hadamard inequality tells me this. And so this already gives me really essentially the bound I want. But I also observe that all the determinants are divisible by 2 to the p minus 1, because if you add or subtract the first row from all the other rows, then all the other rows will be divisible by 2. Each other row will be divisible by 2. So each determinant of Bi divisible by 2 to the p minus 1. Again, yeah, so you have 2 rows of plus minus 1, so everything will be either 0 or minus 2 or plus 2. So it will be right. You can, yeah. Yeah, modulo 2, all the rows are the 1 vector, so the difference of every 2 rows is a 0 vector, which is, yeah. Okay. Good, so every row is divisible by 2, so it's divisible by 2 to the p minus 1, and because of this we could have written that, and this is, so this gives us that the L1 norm is at most, so this gives a L1 norm of this w is at most p plus 1 to the p plus 1 over 2 divided by 2 to the p minus 1, but p is at most t, and this is a monotone function, so we get what we want. To do t minus 1. Okay, so let me, I'll just prove the upper bound, so another 5 minutes, and then we'll make a break. So here is right, so proof of upper bound, and actually it will be in some sort of nice expression. So f of t is at most t plus 1 to the t plus 1 over 2. It's the claim, maybe minus 1 or something, but anyway. So, so here is the proof. So let v1 up to vm, with m being this f of t, right? So these are in plus minus 1 to the t. I take the extremal example. M is f of t. The sum of vi is a vector j, the all-known vector, and no subset positive in each coordinate. Subset means a proper subset. Okay, so let me define Vm plus 1. I want to have some 0 for V. So Vm plus 1 will be minus j. Right? So now the sum of Vi is 0, is a 0 vector. I go from 1 to m plus 1, and no subset. No subset. Sum is 0, right? Because if some subset sums to 0, then also the complement sums to 0. So one of them does not contain j. I delete the one that does not contain j. Then I'll have some subset that together with j is 0. So without j, it is still 1 in each coordinate. It will contradict minimality. Okay, so this is a. All right, so let now ui, u1 up to us will be the distinct vi's, vj's. Okay, VI's. So I just look at all the VI's. I look how many of them are distinct, and I take all of them. And note that S is less than, let's say, 2 to the t minus 1, because we can't have a vector and its inverse, right? So no Vj is equal to minus Vj prime. Otherwise, it would not be minimal, well, at least if t is at least 2 or 3 or something. Anyway. So, and now let xi be the number of times ui appears, so the number of j, so that vj is equal to ui. So now we have something that looks like the cone that we had before. Sum of xi, ui is a 0 vector. Right? That's a okay, so by lemma 1, lemma 2, we know that this vector x, so x1 up to xs is equal to the sum of bi, yi, yi basic in this cone, right? Now the cardinality of I, we know that it's less than S, which is 2 to the t minus 1 here, right? And we know that each yi is basic, so because of this, by lemma 2, I can already, okay, so that bi is positive, and each yi, so we can already make it integral if we want. Integral, and the L one norm of each yi is at most this t plus 1 to the t plus 1 over 2 divided by 2 to the t minus 1. You see the bi's are some positive reals. They are not integers necessarily, so there are some, okay. But now the crucial point, this is trivial, but that took me a long time to realize. So, so the crucial point is that each bi, so these are reals, we don't know they are. The claim is that it's at most 1. You see, because if some bi is bigger than 1, then else we have y, this yi, which will be y1, y2, up to ys. This will give us something that is smaller, so it is smaller coordinate-wise than x1, x2, up to xs, right? Because the bi is bigger than 1, and all the others are also positive. So it means that this gives us really a subset of the columns whose sum is 0. And that's a contradiction. Because, so again, so if bi is bigger than 1, then if I just take yi is 1 times bi, then I claim that this will be some vectors that in each coordinate it will be smaller than the corresponding x, right? Because look at this, smaller or equal. Because look here, I mean the bi is even bigger than 1, so it increases. All the things here are non-negative, right? This is a cone, so all of them are non-negative. And also the other yi's, if we have any others, we don't know that we have, but maybe we have any others, they also increase the x's. So this will be smaller coordinate-wise, and therefore sum of yi, of this yi ui, is also 0, and this is a subset.
The xi's are reals and the yi's are vector. Oh, you wrote yi as a vector.
Yeah, maybe I have here. So when the y appears with this, it's a vector, and when it appears like this, it's a coordinate of y. Maybe it's not so ideal, but yeah. But anyway, let's me. Okay. So so this contradicts is a contradiction. As it gives a subset, a proper subset of the VI's with some 0. Which proper subset? We take exactly UI yi times. We had it xi times in all our V's. We take it only yi times. So this is less, and this is a contradiction. So this gives that each bi is at most 1, and then we just finish, because now by the triangle inequality, the Lm plus 1, which was the L1 norm of the vector x, right, just number is at most the sum over I of this yi, L1, because each bi was at most 1, and we had at most less than really 2 to the t minus 1 of them, and each one had L1 norm this. So this gives the upper bound that we want. Okay. Good. So this is the upper bound. We'll take a break of, we usually say 5 minutes, and really, in reality, it's 10 minutes. You don't have to return. You can't return. I should say that the best joke is going to be in the last minute of the lecture, but of course you can go out and come back just for the last minute of the lecture. That's another possibility. And yeah, so what I'll show is something about the lower bound, and then we'll talk something about the weighted case. Okay, we'll make a break. Lost some 30%, I think. That's okay. But,
Maybe they didn't like
all right. That's right. Okay. And checking, yeah. Okay. So, yeah, so maybe in the lower bound, maybe I'll give a little bit less details. But again, if you want, you can stop me anytime as you've done. So on the lower bound. Okay, so what I want is to use a result. So this is from that paper with Wu, and but it's really following Hastad. And that essentially solves, at least asymptotically, this question about the so-called anti-Hadamard matrices. So what we show is, see, we are gaining. So what we show is the following: that for every k, there exists a k by k non-singular, so a non-singular A matrix Aij, k by k, Aij is plus minus 1, so that the inverse has a big entry. Now let's put the big entry in the first coordinate, because we can put it anywhere. So with a minus 1, let's say in place 1, 1. Okay, so that's a 1, 1 entry of a minus 1. So this will be a k to the k over 2 plus little o k. And this again tight by Hadamard, so up to this little o of k things. So this is an explicit construction of I mean, random matrices will be very bad here, actually. It will not be big. So that's some explicit construction of a matrix with a big entry in the inverse, and as I said, naturally you can call those matrices anti-Hadamard. Okay, so this.
Random triangular matrices.
Well, there are plus minus ones here, so okay, so it is right, yeah.
Below the diagonal, random plus minus.
Then yeah, then things are easier, right? Yeah, for every value of k, the little of k, the error terms fluctuate a little bit. Some of the constructions are based, just the constructions, are based when k's are powers of 2, and then there is a way to play with it. So still, what is here is true always. So you never lose more than. You never lose more than something like 2 to the k or 2 to the 2k, something like this, which is negligible. All right. Okay, so let's believe this. This is really this construction, and you see. So take such an A. So for such an A, if we look, I'll change it soon, but we look at A and we add to it a vector of with zeros here, so 1 and 0, 0, 0, then we know by Cramer's rule that the value of x1, so it will be the ratio between two determinants here, right? The determinant when we delete the first column. I don't worry about signs here, so let's now, right? So
You're talking about
the solution, right? So if we look at this, then so let me, how shall I call this B prime, because I'll change it soon. Then we know then by Kramer by Kramer, we know that the ratio between what I denoted the determinant of B1 and the determinant of B k plus 1, right? So if we delete the last column, this is the determinant of the system itself, of the matrix. And if we delete the first column, this is what we up to sign. Right? So let's put absolute value here. Then this is really the solution. This is x1, right? And we know that x1, this is the first row of the inverse, right? So this is going to be k to the k over 2 plus O of k, because this is big, all right? And because of this, we can also now make this the determinant of when we omit the first column, we can make the determinant even bigger if we want, just by changing each 0 here to the right sign. Right? So that implies that there exists a matrix B now, which is A, and here is 1, and in every place here it's plus minus 1, determined to make sure that when we expand the determinants, then each term will be positive, so that also in B, this determinant, or maybe I'll write it already. Okay. The determinant of B1 divided, so here it was with primes, divided by the determinant of B k plus 1 prime is also big, k over 2 plus little of k. Okay. So we can again change signs. So change signs of columns.
You are gradually now building your counter example.
That's right. Yeah.
So
yeah.
you move from k to k plus 1, but you want somehow exponential super.
Yeah. So far I'm doing something with k because my t will be k plus 6 square root k or something. I'll use something from discrepancy. But yeah, I'm talking about the lower bound, so it will come. I'm trying to build a construction with many vectors. All right, so now change signs of columns if needed, so that unique solution up to scaling of this bx equals 0, right? This is just the linear dependence between them, is positive or non-negative in each coordinate. Okay, so we can do that. And now this means, so we know that this smallest, by what we said before, smallest integral solution. So it means we take the solution, we scale it so that it is integral, and any other integral solution will be a multiple of this smallest integral solution. So smallest integral solution is this plus minus the determinant of bi. Or I goes from 1 to k plus 1 over the GCD of them, determinant of the bi's. And the claim is that that this, so let's call this vector W. So I claim that W1 is at least the same thing, right? Because we know that among these determinants, the ratio between the smallest and the biggest is very, very big. Now the GCD is not bigger than the smallest. So the GCD is at most the smallest. And therefore the ratio between this and the GCD is between the biggest and the GCD is at least the ratio between the biggest and the smallest. So the ratio is big. Okay, so we know that's the integral solution. And if you think what this means is that it gives us something that is pretty similar to what we really want, because so this gives this W, this gives vectors, really V1 up to Vm in plus minus 1 to the k, and m is big, is again is equal to k to the k over 2 plus little of k. The sum of Vi is a 0 vector, right? Just because I take column number I Wi times, right? Okay, so maybe take column number I of B Wi times. W is this solution, right? So then they add to 0, and also no subset sum is 0, because this is a minimum integral solution. A subset would give a smaller integral solution. Okay, so it is no subset sum is a 0 vector. Okay. You can also, by the way, convince yourself, just say it and not write it, that this is really similar to, so this will give you also a, and it's not a surprise because this is based on Hastad, but this will give you a threshold gate that requires large weights. You have to think about it a little bit, but it's, and moreover, the threshold gate requires large weight, even if you just assume how it separates this particular k plus k vertices of the cube. We don't have to look at all the 2 to the k. We just have to separate k vertices in the right signs, and then already we need. But anyway, so this is okay. So we got now really lots of vectors. Their sum is 0, and no subset sum is 0. It looks almost like the things that we want. And there are several ways to go from this. But let me show you one way I like. So now what I want is change
So the problem is just to get the positivity now.
to get the positivity, to change the 0 to 1, to make sure that the sum will be all 1. But it looks that already it's more or less the same thing, right? And here is one way to do it. So change you can change signs of rows. You can do it randomly, but maybe better use okay. So to make sure that sum of each column in absolute value is at most, so I write here 6 square root k. Okay, so maybe I didn't say, so let A be the matrix V1, V2, and so on up to Vm. So this is now a k by T matrix, right? It has by M, a k by M matrix of plus minus 1s, and we know that the sum of the columns is all 0 vector. And now what I want is to change, and the sum of every row is 0, right? And now I want to change signs in each of the columns so that each column in absolute value is small. So I could change randomly, and then it will be 6 square root k square root log k. There are only k distinct columns here, right? So they are k plus 1. So although M is big, they are just repetitions of the same things. And this is basically using the 6 standard deviations. So this result of Spencer and Gluskin, and if you want proof of Louvet and Mecca if you want to do it deterministically. Yeah, but you see, so I said it, but so M is large, but the vectors are repetitions, so there are only k plus 1 distinct vectors here. Only k plus 1, right, yeah. So M is very big, but M is just repetitions, right. So you can make every sum an absolute value pretty small, and now you can add to A 6 square root k, roughly, maybe you have to keep some parity, but let me say 6 square root k roughly rows to get, so now it will be A prime, it will be Aij, it will be T by M, T is now k plus 6 square root k, so I just took A here, and I added to it some additional rows here, so that the sum now in each column is 0 exactly. So I want to, and the sum in each row is also 0. So A prime is like this, with sum of each row equals sum of each column equals 0, and no subset of columns has sum 0, is of course because no subset even in the top part has sum 0. Okay, so so this you can convince yourself that you can do. I think it's believable. There are several ways to show that that indeed you can do it. Okay. So, right, because we just need, in the matrix that we are adding, we know how many plus ones and how many minus ones we should have in each row and each column. And so you can, one way to do, so there are network flow things tell you for which values there are matrices with given row and column sums. You can apply this, or you can do it directly. There are many ways. Anyway, so this is true. Okay, now now I want to get the positivity somehow. So so we have okay. So call columns of this A prime, and let me call them again V1 up to Vm. Right? So it's an abuse of notation, but I don't want to carry primes. So these are the columns of. In this, the sum of them is a 0 vector. The sum of coordinate of each vector is 0, and there is no subset sum, which is 0. All right, now just omit one of them, omit Vm. Okay, so now sum of columns is, so it has, we omitted one vector, so really now it has a -1 in t/2 coordinates. And yeah, but I change it, so now t is k plus 6 square root k, but it's not a big deal, right? Yeah. And when you add 6 square root k, you also should keep the parity, so you should make sure that the number of rows is even, if you want. Never mind, because otherwise the sum cannot be 0. So now after we deleted something, we have the sum so far is just the negation of the vector we deleted, right? So it has a -1 in t/2 coordinates. Let me assume that they are the first ones, and +1 in t/2. And now add 2 vectors, and 2 additional vectors instead of this that we deleted. So now I want to have the sum exactly 1 in each coordinate. So the 2 additional vectors, well, in the top I don't have a choice, right? So I have to make the sum 1, so I have to add a +1 in the in both of them. But here I have to keep the sum as it is, so I have to do it plus in one of them and minus in one of them. So let's do here a +1 in t over 4 and -1 in t over 4. Doesn't really matter. It has to be in some positive. Okay, so this is t over 2. And here it is -1 and +1. This t over 4. Okay, so we call this guy a Vm now, the new Vm, and this one is Vm plus 1. So still, we have lots of vectors. And now the sum, close to finish it. So now the sum of all these Vi's, I goes from 1 to m plus 1, is j, right, is all one vector. And I claim that no subset, so we want to show that no subset is positive in all coordinates. It will be more convenient to look at the complement. So we'll show, we'll just note, I mean, it's obvious, we'll show that no subset is at most 0 in all coordinates. No non-empty subsets, right? If we have something that is positive in all coordinates, then the complement of it has to be at most 0 in all coordinates. Well, if there is such a subset, it cannot contain one of these guys because those have sum of coordinates positive, and all the others have sum of coordinates 0 exactly. So we cannot have the sum of coordinates will be. Okay, so such a subset cannot contain Vm or Vm plus 1. It cannot contain any of them. Again, because the sum of coordinates of Vm and of Vm plus 1 is positive, the sum of coordinates of every other vector is 0. So if we will contain one of them, the sum of coordinates will be positive. But then it cannot be at most 0 in each coordinate. And therefore, on the other hand, hence, so it's a subset of V1 up to Vm minus 1. And it has to be at most 0 in each coordinate, the sum. So it has to be exactly 0, because, again, the sum of each column is 0. So the sum of everything is 0. Therefore, nobody can be really negative because that will force someone to be positive. Okay, so hence sum has to be 0 actually, but this we know that does not exist, right? Because this is what we got from this is contradiction. Okay, so we know the lower bound basically up to showing this construction, which will need another hour or something. We won't do that. Let me say something quickly about the weighted case. Not say much, it's not. But somehow the weighted case maybe is more realistic because first, indeed, you have parties. So parties really do not change the situation by much. These are just weights on the rows, and basically everything works. So weighted version. Okay, so you have parties. They correspond to weights W1. W1 up to Wn on rows. Because a party votes all together, the weight or the size of each party is what it is, and it gives. This will not make things really different. What makes a big difference is issues also may have different weights. columns. So these are weights on columns that we'll call Z1 up to Zm. So really what is now the question, if we have weighted issues and we have parties, that we have a matrix A. This is Aij. It will be an M by M matrix, and all right, so this is this matrix, and we have weights corresponding to the sizes of the parties, Wn, and here we have Z1, Z2 up to Zm, corresponding to the issues, and Q, a set of issues, so Q, a subset of M, is winning if and only if, so again, we look at the sum of Wi, right? Write it like this, the sum of the sizes of the parties for the parties that support the agenda. So which parties support the agenda? This is over all the i's, so that the sum of A, I, J, J in Q, Z, J is positive, right? Those are the i's for which you have in the weighted majority the parties, ith party supported, and we want to get majority, namely we want to get more than half of the total weight. Right, so this is the question now, and it's not too difficult to show. And again, I'll not show you a proof here, but so write it as another proposition. So the following is true: if in this version, if n, the number of rows, is really small, so if n is at most 3, is at most 3, then it's trivial. So this part is very easy. Then if there is a winning agenda, so the total number of parties you have is now at most 3. Then if there is a winning agenda, then there is one which is very simple, in fact consists of one issue. You just have to decide that, I don't know, no nuclear weapons to Iran, and that's the only thing we care about. And this is, okay, so then there is an agenda, a winning agenda, a winning Q of size 1. And therefore, of course, it means that computationally this problem is not so difficult. We just have to see if there is one single column or issue that more than half of the weight supports. Okay, on the other hand, if that's a little bit more difficult, but it's also not too difficult. So if n is at least 4, or if n equals 4, but it's the same. So for every n that is at least 4, so first there are then for every p there is an example. So think about p as a big integer. So really now the supremum, so these numbers that were g before are not finite anymore. So for every p there is an example with a winning agenda, and all winning Q of size bigger than p. So for every p, we can make it so the number of issues can grow as much as you want, and still. In fact, and that's a pretty simple example. In fact, the simpler examples will have just one important issue, so one big z, one big weight, and all the others can be still small, just one. So we can do it with one big weight. There is one issue that really everybody cares about a lot, the Palestinian problem, if you want, again, the Israeli politics. All the others are kind of comparable, and then things become already very complicated, or we need, right, yeah, so it is, okay, and also, for each fixed n, so it's not fixed parameter tractable anymore. For each fixed n bigger than equal than 4, then deciding if there is a winning Q is hard, is anti-complete. So even if just you have 4 parties, then deciding if there is a winning agenda is already complicated. And again, it's like one of these proofs of NP-hard, so it seems that nobody is coming for the joke. Yeah, I hope the expectations are not so high from this. It's not so, but let me indeed finish with this. So this is a quote. It's a correct quote of someone in Weizmann Institute, actually, who is involved in administration there. And he said once that, so he's talking about committees, and he said that every committee should have an odd number of people. That makes sense, right? You want, and also he said that committees of size 3 are too large. So, okay, and so if you want, that's it, and it's a true story, I mean, and what you see here is sort of a mathematical proof that for some model, having 3 parties is still okay, but having 4 parties or more is already too large. And with this, I'll finish. Thanks for your patience.